Greetings and welcome once again to my new calculus channel. My name is John Gabriel, and today I'm going to be continuing with part 2 of my series on how you got numbers. So let's continue. Now, in the previous video, I talked about what is a ratio and why do we need ratios in order to understand numbers. Well, I also gave you an example of how somebody without the knowledge of numbers could actually communicate the idea of a certain length using a reference magnitude, okay? In this case, his hand. So you can go over the first video. It's advisable that you do. Please note that set theory is not mathematics, neither is topology, neither is real analysis. That is just anti-mathematical BS. Say no to that, okay? It's been going on the last 200 years, but it has nothing to do with mathematics at all. And it cannot be considered mathematics in any sense of the word, because mathematics is the abstract science of measure and number. Now, let's continue on with the second video. Numbers arise naturally from ratios. Okay, so the consequent and or equal parts of the consequent measure the antecedent. Okay, so what does that mean? That means if you had, let's say, this ratio and this one, like that, what you could do is you could say, right, both of these are measured by the same magnitude. Let's say this one. Okay, so this measures that one without remainder. So it measures that one and that one without remainder. Okay, I could have made that one slightly longer. There you go. Okay, so it measures, it means the ratio has quotientness and it is measured by the same magnitude. Similarly, this ratio here has quotientness too, because we can measure the antecedent. By the way, that's called the antecedent. This part is the antecedent, or the grandpa of the numerator, and the consequent, the grandma of the denominator. Okay, so parts of the denominator, this part, half, measures this, or a quarter, or any other equal part of this consequent, which acts like a unit or a measuring magnitude, fits exactly into the consequent. Okay? So in part 2, we take a step further. We know that a ratio with quotientness has an antecedent and a consequent that's measured by a common magnitude without remainder. However, we do realize that ratios can be in proportion to each other. So for example, you have this ratio and this ratio, okay? And although they're different ratios, of course they're different because look, this one is this long and this one is this long. They have a common measure, and we'll see what their common measure is. And that is that their antecedents are measured by half of their consequence, okay, or an equal part of the consequent. So if we want to talk about the relationship between the aliquot parts of a ratio without the diagrams, then we need to enumerate them. How do we do this? So for this, we need to assume some kind of scheme where we can name these parts, okay, and we can enumerate them. So we assume that the common magnitude is the unit, and we call it by the name of 1. It's actually 1 over 1, but we call it by the name of 1. And so we'll see that 1 is equal to the measure of this ratio, okay? And similarly, we do the same for multiples of this antecedent. So instead of having one of these, we have 2 or 3 or 4. These are all lines, okay? All lines. And we call these 2, 3, 4. So now we have a way of naming enumerating the antecedents. But you have to be careful because some ratios, although in proportion, like this ratio here and this ratio here, because this here, its measure is 1/2, and the measure of this one here is 2/4. But in algebra, 1/2 is equal to 2/4, okay? Because we don't care about the size of the antecedent or measuring unit anymore. We just treat it as an abstract size, and we treat its equal parts as abstractions as well. Okay, so and since we're able to enumerate these, we can now, or since we are able to name these numbers, we can now enumerate the consequents and the and the antecedents. Okay, using these class of numbers, which we call multiples of the unit, or those that are taught to you as by your idiot professors as natural numbers. Okay, so you have natural numbers, and then you have what they call rational numbers. But truly speaking, natural numbers are part of rational numbers, and there really is nothing else above this, by the way. So those fools might say I for irrational numbers and real numbers, but these outer bands are a bunch of nonsense. They don't exist as well-formed concepts. The only numbers you have are fractions. We'll get back to that in a moment. So we can denote the enumeration of these quotient ratios using these antecedents, or whose antecedents are multiples of the unit. So we can give a name to the measure of any quotient ratio by writing the enumeration. So for example, if the antecedent is P and the consequent Q, we can write the enumeration as P over Q with the corresponding consequent. And we call these natural numbers. Now take a look at this ratio down here. Okay, it's actually a ratio of ratios where the unit is this line here. In this case here, we call the measure of this a fraction, okay, because the first part is 3. Okay, that's 3 over 1, in fact, 3 over 1. And the second part is 4 over 1. And so the complete measure is 3/4. I guess I have to reload this just so that we can get the original part again. Hang on a second. We'll get there. All right. So as we see, this is 3 over 1, and this is 4 over 1. And as a fraction, it's called 3/4. Okay, so the measure of the ratio of natural numbers in the above example is called a fraction. And I'm going to stop here. And the next video, we're going to talk about any ratio whose aliquot parts, meaning the antecedent and consequent, cannot be enumerated. So we'll leave that for that section. Now, what that means is that you'll have a ratio like this, where these two have no common divisor or magnitude. Okay, no common magnitude that measures them without remainder. Okay, in other words, what might happen is that you might take this guy here like this, or any equal part of it, and you might go 1, 2, and a little bit here, and you can't really find this little bit here, which means this ratio doesn't have quotientness. If you're not already a subscriber, people, become a subscriber to my channel. Also, follow me on academia. This is my academia channel. I should have brought it up before I started the video. There are hundreds of free articles. And also buy my books on Amazon Kindle so that you can support me. Believe it or not, I receive less than 12,000 as a pension every year. So I'm way below the poverty line. It's hard, and I'm doing this for you. I have no children. This is a labor of love for you. This book here that I've written, you can purchase it without watermark on Kindle, or you can get it free with a watermark on my academia.edu. It's the most important book ever written in mathematics, even more important than the new calculus, okay? Then what is the new calculus? Because without this, you cannot understand mathematics. It doesn't matter whether you have 10 PhDs or 1 or any other degrees. You're an idiot if you do not know what is in this book. You can't even begin to say that you're a student of mathematics. Of course, you should never call yourself a mathematician unless you've produced great works. And I'm sorry, a PhD is insufficient to call yourself a mathematician. On academia, you will find all the articles. Here's where you can download this article free. Okay, learning the correct way, free forever because it is priceless knowledge. So, become a subscriber to my YouTube channel, click like, follow me on academia, buy my book to support me. And you can also become part of my members only group for $4.99 a month. Currently, I have no more than about 20, so I don't have a lot of members only. But I'll share information on my members only channel, which you will not get on a normal subscription to my channel. Very well then, my name is John Gabriel. Till next time, goodbye.